In Unit 2, Note C, we're going to talk about the arrangement of electrons. This is the beginning of quantum mechanics, a notoriously difficult field of science. We're going to start with something called an electron configuration. A configuration shows the setup of something, so we're going to look at how the electrons are set up inside the energy levels of an atom. What makes quantum mechanics so difficult is that you can't just pinpoint one location for an electron. There are several reasons for this. An electron would be in a completely different place by the time we were able to calculate where it was. The other thing is there's something called Heisenberg's uncertainty principle, which basically says you can't know both the speed and the location simultaneously for a particle. So this leads to some more calculus-driven wave functions. And what we're showing with the orbitals that you see here is the areas where you will probably find the electrons. So this is basically a probability calculation. Where would we find the electrons? Somewhere in the shaded regions, but not in the white regions. We have 4 different types of orbitals, S, P, D, and F, all with different shapes. Regardless of the complexity of the shape, every orbital holds up to 2 electrons. An orbital could be empty, it could hold 1, or it could hold 2, but never 3. It may appear that both electrons would be inside of the S, and then for the P, 1 electron in each lobe, and that is one possibility, but it's also possible both electrons are in the same lobe. When we get to the more complicated shapes, some of the lobes have to be empty. It could also be possible both electrons are on the same lobe. All we know is that those 2 electrons are floating in the shaded areas somewhere, just not in the white space. Every orbital, regardless of the complexity of the shape, has exactly or up to 2 electrons. An electron configuration is sort of like the mailing address for an electron. It starts off broad, saying generally what area we would find it in, kind of like the state of California. But then we start to get in closer and more narrow. Maybe we can narrow down to a county or a street or the exact house. We're going to do the same thing with an electron. We'll say where, what energy band the electron is in, and then what type of orbital it's in, and then which of those 2 electrons might it be. So it starts out broad and gets more narrow. There are 4 main components to any electron configuration. Our first component is the principal quantum number, abbreviated with a lowercase n. The principal quantum number is going to describe the energy level. Remember that we said that the lower energy levels were closer to the nucleus? So we have our first energy level being the one most central to the atom. And as we go out further, the next energy level would be a higher principal quantum number. And you can go all the way out, having more and more principal quantum numbers, all the way up to number 7. The known atoms of today have 7 energy levels. Well, some of them have up to 7 energy levels. The further away from the nucleus, the higher the energy level. This goes back to what we talked about with light. An electron is lazy and it wants to be in the energy levels that are close to the nucleus. And then as the lower energy levels fill, it will build out to the further energy levels. Those would have more energy. The scientific principle responsible for this, or I should say that explains this, is called Aufbau's principle, which basically states that electrons like to fill the lower energy levels first. The second electron configuration part is the angular quantum number. So this would be a sub-level. So we already know that an electron would go to one of the 7 bands, and then within those bands, we can have up to 4 different sub-levels. These sub-levels are the shaped orbitals that we've looked at before. S being spherical shaped, P being dumbbell shaped, and then you have those complex flower-like shapes for D and F. There is a catch to this though. Not all 7 energy levels have all 4 shapes. There's a rule that states the number of sub-levels must equal the quantum number. So if the quantum number is 1, I can only have 1 shape. What was the lowest energy shape? It was S that would fill first. So the first energy level can only have an S shape. The second energy level could have two shapes. So it can have S and what would be the next lowest energy level? P. Or I shouldn't really be calling them energy levels, but the next highest orbital. So 2 can have S and P. If I had 3 energy level, or an energy level of 3, n equals 3, I could have S, P, and D. And then from 4 on, I can have all 4 shapes. But the number of sublevel is equal to the quantum number. So the first 3 levels do not have all 4 shapes. When we write out the electron configurations in a bit, we're going to combine the energy level and the sublevel. So we could actually write 1s as an orbital, 2s as an orbital. I would want to also write this as 2p to represent the orbital. You always combine the principal quantum number and the angular quantum number to represent a more precise orbital. Remember that each shaped orbital had a different number it came in. For example, S, there's only ever one of. How many versions of the P shape are there? And then how many versions of the D shape? And then how many versions of the F shape? So there's 1 S, 3 for the P, 5 of the Ds, and 7 of the Fs. Anytime you have a p orbital, it will come in a set of 3. One would be oriented on the x-axis, one on the y-axis, and then one on the z-axis. So we have these different varieties of the orbitals. That is our third quantum number, the magnetic quantum number. It's going to describe which of the orbitals the electron is located in. Is it on the x-axis version or the y-axis version? That's going to be determined by the magnetic quantum number. The abbreviation is actually M with a cursive L. Our fourth and final part of the electron configuration is the spin quantum number. Now that we've got it all the way narrowed down to one very specific orbital, even if I know I'm in the second energy level, P shape, it's the one on the x-axis, there could still be 2 electrons bouncing around inside of that orbital. So how are we going to tell those two apart? Well, they would always be spinning in opposite directions. There's actually something that says that the electrons would never spin in the same direction if they're in the same exact orbital. So since they're spinning in opposite directions, that's what we can use to define them. Hence the spin quantum number with the symbol M with the subscript of S being our fourth number. A lot of times this is represented with arrows. We're going to look at something called an orbital diagram soon. And in that, every electron would be represented with an arrow, and you would never want to put 2 arrows going the same direction in the same exact orbital. They would be going in opposite directions. Notice as we finish the fourth quantum number that the numbers aren't actually always numerical. It's more of a saying, a phrasing. The electron configuration's job is to pinpoint the location of the electron, and that may look a little bit different at each phase. The principal quantum number would tell you the energy level where you can find the electron. Then we would narrow that down to the shape with the angular quantum number. Then we would identify which version of the shape we are in with the magnetic quantum number. And finally, we would identify which rotation of the electron we were talking about with the spin quantum number. And that will get you all the way down to an individual electron. With all these different quantum numbers and rules at play, we've got a few tables to help us organize all of this. Let's start by figuring out which sublevels could be present for each energy level. Say we have a principal energy level of 1, the very first energy level closest to the nucleus. The rule was that we can only have the number of sublevels that equals the principal energy level, which means an energy level of 1 can only have one shape. And the sublevel that would fill first is the S sublevel. So we would have a 1s orbital. If the principal energy level is 2, we could have 2 shapes. So we can have a 2s, but also a 2p, the next shape that could fill. With an energy level of 3, we could have 3 shapes. So we'll have a 3s and a 3p, but then also a 3d. And then finally, once we get to principal energy level 4, we can have all 4 shapes. So again, we're going to combine the principal number with the sublevel for S, for P, for D, and for F. In theory, principal energy level 5 could have 5 shapes. So if we discovered more atoms, we may need to introduce a G orbital, or G sublevel, I should say. But as of right now, all 118 elements are able to work with just the sublevels going up to a sublevel of F. So we're going to stop there, but know that principal energy level of 5, 6, and 7 can also hold all 4 shapes, and then theoretically some more. Now I want to talk about the magnetic quantum number. All I really want to do at this level is make sure that you know how many shapes accompany each type of sublevel. If I have a 1s sublevel, because of the s, I will have only one orbital. That is consistent anytime I have an s. Just because it says 2s doesn't mean that there are 2 orbitals. The s is always one orbital. What does that 2 represent? That is the principal energy level, which represented the distance from the nucleus. So it's still a spherical shape, just like it was on the first energy level, but now it's just located in a further energy level. When we look at the 2p, p's always come as 3s. Regardless of it again being in that second energy level, it is still going to come as a set of 3. How many orbitals would be in the 3s? Only 1. So what does the 3 represent? What is the 3? Again, the distance from the nucleus. So now we are just another row away from the nucleus, but the s is still a single sphere. How many orbitals would there be for 3p? 3. Not because of the 3, but because of the p. How many orbitals would be in 3d? D comes as a set of 5. The 3 again represents the distance. Let's see if you can do this orbital counts for energy level 4. How many s orbitals? How many p? How many d? How many f? S always comes as 1, p is 3, d comes as 5. If you remember the pattern, f comes as a set of 7. So to sum this up, the number of orbitals is solely dependent on the shape. S always has 1, P always has 3, D always has 5, and F always has 7. That is how those orbitals come, as a set of this given amount. The numbers that are paired with these sublevels represent the principal energy level, or the distance from the nucleus. So as I go down this table here, I'm getting further away from the nucleus. But those sublevels consistently come as a set of 1, 3, 5, or 7, no matter which sublevel they're on. I do want to warn you that the orbitals, or the magnetic quantum number, may look slightly different in your AP or IB classes. All we're doing right now is counting how many options there are, but technically the magnetic quantum number should tell you which of those options the electron is found in. Just to give you a heads up that you may see this look a little bit differently, where you're actually writing which orbital it's in. Let's focus solely on the sublevels for a second, the S, P, D, and F. How many orbitals came in each one? S has 1, P has 3, D has 5, and F has 7. You've got to know these numbers, 1, 3, 5, 7. Now I want to determine how many electrons could be held in each sublevel. So let's think back to the beginning. How many electrons could be in a single orbital? Every orbital can hold 2 electrons. So with S having a single orbital, it could only ever hold 2 electrons. But if P has 3 orbitals, each of which can hold 2, I could get up to 6 electrons. With this pattern, how many electrons would D hold? 10. And then F, with 7 orbitals, could hold 14. These are super important numbers that we're actually going to write on our electron configurations as well. These will become a kind of a superscript that we put on that orbital where we were writing 1s. I could then indicate that there are 2 electrons in the 1s. And this is exactly what it's going to look like once I start writing electron configurations. Before we get to actually writing electron configurations, there are 3 important rules that we need to go over. The first is Pauli's exclusion principle. This basically says that every electron has a very special set of 4 quantum numbers. You can never have the same exact 4 quantum numbers for any 2 electrons. So although 2 electrons could be found in the same energy level or distance from the nucleus, they could even be found in the same shape, maybe both in a p orbital, and they could even both be in the same p orbital, having the same magnetic quantum number, but they still would be spinning opposite directions. So this is something that we want to follow when we start indicating the spin with the orbital diagrams, that we always make sure that if 2 electrons are sharing an orbital, they're spinning in opposite directions. Otherwise, we would violate Pauli's exclusion principle. Next, we have Hund's rule. This is based on the premise that electrons are all negative and would therefore repel each other. There is a catch, because above all, electrons are lazy. So assuming that we have equal energy, maybe say we're looking at 3 equal energy p orbitals, electrons would spread out into the p orbitals before they would go back and pair. I'm going to use a little peek at looking at the orbital diagram here. So an orbital diagram would have a line for each of the orbitals. So let's say these are 3p orbitals. If I had 1 electron, I would draw it as 1 arrow into one of the lines. Then if I had a second electron, I would put that in the next orbital over. I would not pair it in the same orbital when I had an equal energy empty orbital right next to it. Think of this like you're getting on a bus. You're going down the aisle, you got the same seat to your right and your left that are right next to each other. That would represent being of equal energy. You look to your right and there's a smelly hobo. You look to the left, you got an empty seat. Where are you going to sit? You would rather sit by yourself because you are repelled from said smelly hobo. I know that's not the best example, but electrons don't like each other. So just think of them trying to get away from each other. They don't want to be in the same orbital. So they would spread out. If I had a third electron in the example I'm drawing here, I would put that then in the 3rd energy level. If I had a 4th one, I would fill this energy level before I moved on to any of the d orbitals. I'm going to fill up the p first. So then I would come back and pair, and I would make sure I went the opposite direction. The 5th one would fill in opposite direction here, and then complete the shell by putting the last electron in there. So you kind of fill in a very deliberate order in order to follow Hund's rule. Hund's rule also discusses the orientation or the up versus down of the arrows as well. A singly occupied orbital would be what I've drawn here. Each orbital has a single electron in it, and it says those should have the same spin. And then it also talks about if I go back and pair, that they would have opposite spins. This has more to do with magnetism than Pauli's exclusion principle. This is just describing the way that electrons would orient themselves. So we can actually follow both rules at the same time, which is nice. But Hund's rule is all about the electrons being selfish and spreading out, whereas Pauli's exclusion principle is about making sure that no 2 electrons have the same quantum numbers. And last but absolutely not least, actually probably the most important, we have Aufbau's principle. Aufbau's principle tells us exactly how the electrons will fill. This is the exact reason why the electron configurations have to go in a very specific order. And we're going to go over that order here shortly. That's kind of the hard part. Aufbau's principle says that electrons are lazy. They will fill the lowest possible energy level. So the hard part is figuring out exactly what the lowest energy level is. Like, what is that progression from low to high? This is one version of the order. It's not my favorite way to do this, but it does work. What you would do is you see we've numbered from 1 to, now you could go all the way to 7. This seems to be an older version. And then you can go out, since 1 only has one shape, you would only write 1s. Since 2 has 2 shapes, you could write 2s and 2p. 3 has 3 shapes, and then 4 has 4 shapes, and so on. So you could carry all the way down to 7f. So to use this method, you would either have to have this, like pull up this guidance, or know how to make it, which is what I just went over. Then you're going to go diagonal. So it's really important that everything is lined up. Like use a ruler if you're making your own. And you would start at the very top and read diagonal. 1s would be the first orbital, then 2s would be the second. 2p would come next, and then 3s. After that is 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 4f, 6d, and so on. So you would just read across, and that's going to give you the order of filling. But you've got to be very careful and deliberate. This order is also, or this version of determining the order is also not my favorite because it makes it hard to pick up in the middle. I'm going to teach you a shortcut that's, first of all, a little easier than this in the first place, if you ask my opinion, and it also makes it really easy for a shortcut that I'm going to teach you soon. The way that I prefer to do electron configurations is using the periodic table. So there's a lot of patterns on the periodic tables, and this is one of the best ones. You do have to know a few things about how this is set up. So first, let's talk about the blocks on the periodic table. Your first and second columns make up something called the S block. Then you would have the transition metals next, which would make up your D block. On the right-hand side of the periodic table, those 6 columns would make up the P block. And then the 2 rows that were kicked out of the periodic table down here on the bottom make up your F block. The numbering is also interesting. The S block starts at 1, since if I have a principal energy level of 1, I can only have one shape. So notice how helium actually would kind of make more sense to draw over in the S block. It's considered a 1s element. The P block then would start at 2, since helium doesn't count. And with a principal energy level of 2, you would have 2 shapes. You can have a 2s and a 2p. The D block starts at 3, and this comes from the idea that with the principal energy level of 3, you would have 3 shapes. So it means that you have to have a 3s, a 3p, and a 3d. This does create a complication for the shortcut, because notice how it's not in line. If you go from 4s, you have to drop down to 3d. So notice that the 3d orbital is on the 4th energy level. So it's going to be a little tricky when we start actually writing the configurations. On that same token, the F block starts at 4. Since to have 4 shapes, I would need to start with the 4th energy level, or the 4th energy level is the first one that can have 4 shapes. So that means I should have a 4s, a 4p, a 4d, and a 4f. But it gets really tricky because if I'm going from 6s, that's where the 4f block would connect to. So the 4f actually kind of belongs right here in between 6s and 5d. So we've got to be really careful, because basically what we're going to end up doing is reading from left to right and top to bottom. As we go across, we have to be really careful of the D and F numbering. Okay, let's go over the order. I'm going to do this once, but feel free to rewind as many times as it takes. The idea is that we start here at the top, and we would read from left to right, top to bottom. So my first orbital would be the 1s. Then I'm going to start on my second energy level at the left. My second orbital would be 2s. I'm going to go across, and my next orbital would be 2p. Now time to start on my third energy level. I would have 3s and then 3p. Notice how I didn't cross 3d as I went from the s to the p block. The d is after the 4s orbital. That is on purpose. That's why the periodic table is kind of a good trick. So we've got 3s, then 3p, and then you would come to 4s before you get to 3d. And then 4p, and then 5s, and then 4d, and then 5p, and then 6s. Careful, because from here we drop to the f block. We would have 4f, and then we would continue back up here to 5d, then 6p. Then on our last row, we have the 7s, and then this drops here to the 5f. Then we start back up here at the 6d and finish with 7p. That is the order that the electrons will fill, and that is the order that we have to write the orbitals. There's one more cool trick on this periodic table. Earlier we determined the number of electrons that could be in each of the orbitals. Since S only had one orbital, it could hold 2 electrons. The S block is exactly 2 electrons wide. The P orbital with 3 orbitals could hold 6 electrons, and the P block is exactly 6 blocks wide. The D block is exactly 10 blocks wide, since it can hold 10 electrons. And the F block is exactly 14 blocks wide, since it can hold 14 electrons. That is not by coincidence. Alright, it's time to put this all together. We're going to write electron configurations. If you're feeling tired already, take a break, come back to this, because this is what it's all about, writing these electron configurations. Here we go. The first configuration we're going to do is for helium. So the first thing that you want to do is find helium on your periodic table. My periodic table is super small, so I would recommend following along on your own periodic table. It might even be a good idea to put your periodic table inside of a sheet protector and then getting a dry erase marker so that you can draw over it and then erase it and keep using that over and over again. So we found helium on the periodic table. We're always going to start at the first block. Start with hydrogen, basically. And you're going to go from hydrogen to helium. If you remember, that was the 1s orbital. To get to helium, we went through 2 blocks. So we're going to use a 2 exponent to indicate the 2 electrons that would be represented there. So the electron configuration for helium is 1s2. You stop where the element is. So that's all there is to helium's electron configuration. Let's try one a little bit longer. Let's do boron. Again, the first thing that you want to do is find boron on the periodic table. Now we're going to start up at the top. Just like last time, we go through the 1s and we go through both boxes. So we'll use the 2. Now you're going to go to the second row and go through the 2s orbital. And again, we're going through both blocks, so we'll use the 2. Now we'll go over here, and this was the 2p section on the periodic table. But we're only going through one of the blocks, so we'll put a 1 there. Yes, P can have up to 6, but it only has as many as you need to get to the element. So since the element boron is the very first element in the P section, we only need 1. Let's take a second to think about what we've written so far. With helium, we had an exponent of 2. And with boron, we have an exponent of 2, 2, and 1, which would total up to 5. Notice that boron is the 5th element on the periodic table. And remember, the atomic number would represent the number of protons, which would be equal to the number of electrons for a neutral atom. So what we're really writing as these subscripts are the electrons. We're writing where each electron can be found. Helium would have 2 electrons in the 1s orbital, and that's it. Boron would have 2 electrons in the 1s orbital, it would have 2 electrons in the 2s orbital, and it would have 1 electron in the 2p orbital. We are writing out how these electrons are spaced inside of the atom. Now let's try neon. Neon is all the way at the end of the second row. So again, starting from the beginning, you're going to go through your 1s orbital, both boxes. So use the exponent of 2. You're going to go through your 2s orbital, both boxes. So again, we'll have a subscript of 2. And then when we get to the 2p orbital, we're going all the way to the end, which means we're going to go through all 6 boxes. So my 2p orbital would have a superscript of 6. So 6, 7, 8, 9, 10 electrons, which is exactly how many electrons neon should have. Now on to aluminum. Aluminum is in column 13, but it's in the 3rd row down. So starting from the top, 1s, we're going through both boxes, so we're going to use the 2 superscript. Then we're on to 2s, again both boxes, so again a 2 superscript. The nice thing about this is it is kind of repetitive. So then we get over here to 2p, and we would go through all 6 boxes. We haven't reached our destination element yet. Now we're going to go into the 3rd energy level. And we're going through both boxes on the s, so s2. But then when you get over to the p, it's only 1 box. So we're on the 3rd energy level, shape p, but only 1 electron there. And if you totaled up all of these superscripts, you would get the number of electrons aluminum has, which should be 13. So now that you seem to be getting the hang of things, give uranium a shot. By the way, uranium is way down here. All right, that's a tough one. Let's do this together. From the top, we're going through the 1s orbital, both boxes, the 2s orbital, both boxes, over to the 2p orbital, and we'll go through all 6 boxes, onto the 3s, where you go through both boxes, so we've got the 2, and then over to the 3p, and this time we're going through all of them, so we've got our 3p6. Now on to the 4th energy level, which is where things get interesting. So first, so far so good, the 4s we're used to, which would have the 2 boxes. But remember, you have to be careful here, because as you go into the d orbital, that's actually the 3rd principal quantum number. You have 3d as your first energy level in the transition metals. And there are 10 boxes there that we're going across. So we'll use a superscript of 10. Then as you go back to the p orbital, we still have that as the normal column number, or row number, period number. So we had 2, 3, 4. We're still in 4p. The s and the p should follow the same principal quantum numbers, whereas the d is going to be offset by 1. So we're at 4p to get all the way to krypton. Now we're going to start at the 5th energy level. So we'll have 5s, go through both boxes, superscript 2. Now as we go into the d, what principal quantum number would we have for this section? It's off by 1, right? So it would be 4d, and then we're going across all 10 boxes. But then remember, you're going back up 1 for your p, so it would be 5p across all 6 boxes. Now we're really going to get interesting. When we go into the 6th energy level, you have to not only remember d is off by 1, but you also have to remember f belongs right here. So we're going to have to go from my 6s down to that f block. First, let's write 6s2, and now let's start at our f block. F starts at 4. It's actually offset by 2. So we're going to have 4f, and then remember f had 7 orbitals, so it can hold 14. We should have 14 boxes for f. Then when you end here, if you look at your atomic numbers, it picks up back at the 5D section. So next we'll have 5D10. And then remember from D, you're going up one even more. So you have 6P6. And then finally, we're in our last period. We have the 7S, which we're going across both boxes. And then just like after the 6S, after 7S, you've got to come down to the F. But now we're in the second row. So this would be our 5F. Because if we start at 4F, the next one would be 5F. But careful, because we're approaching our target element. We've got 1, 2, 3 boxes in the F. So this would be 5F3. And then we're done. That is our super long electron configuration, which pinpoints the location of every electron inside of a uranium atom. You might have noticed by now that not only is it slightly repetitive, it is kind of exactly the same as you go through the same exact elements. Like, there has to be a shortcut, right? Well, there is. There's something called the noble gas configuration. So say I wanted to do it for uranium, I would look at the previous noble gas. So what comes before uranium noble gas-wise? That would be the radon. So I can abbreviate everything up to that position, which would be my 6p6 position, by simply writing uranium. So the noble gas configuration for uranium, I could write radon. Sorry, I keep saying radium. Radon. And then you do have to start the last row from scratch. So that we would write the 7s2 and the 5f3. But we can abbreviate everything up to that noble gas just by writing the noble gas in parentheses. Be careful that if it asks for the complete configuration, it's asking for that gigantic thing in blue, the entire thing. But if it doesn't specify, you're more than welcome to use the abbreviated version. Let's practice the abbreviated version a little bit more. First, let's look at helium. Since helium is a noble gas, we could abbreviate its configuration by itself. Just remember that you always want to put the noble gas in parentheses, or brackets, I should say. So that could be our abbreviated configuration for helium. Next, we would have boron. So boron, that's right here, and its previous noble gas would actually also be helium. But there's more to it, right? Because helium had a few more electrons. So that'll take care of everything up to helium, but then you also have to go through your 2s and your 2p. In the 2s, we had just we had 2 electrons, and in the 2p, we had just 1. So we would write out that entire last section, that last energy level, but we can abbreviate the first energy level with the helium. That might not seem to save us a lot of time towards the top of the periodic table, but it definitely helped with something like uranium, right? Now let's try aluminum. What noble gas would you use for aluminum's abbreviated configuration? The one before it would be neon. So I'm going to write neon in brackets, and then start with the next thing after neon. Over here in our third energy level, we'd have 3s2, and then when you get over to 3p, you only have 1 block, so we'd have 3p1. Next, I want to talk about the electron configurations for ions, but don't worry, we'll stick with the abbreviated version. Let's look at nitrogen. So the noble gas prior to nitrogen would be helium. And if I was writing the electron configuration for the regular nitrogen atom, I would go down to 2s2, and then with the p blocks, I'd go 1, 2, 3 blocks in, so I'd have 3p3. Now let's talk about what this charge means. A -3 charge means it has 3 extra electrons. So instead of 3p3, I'm going to add 3 more to that to make it like 3p6. that would actually carry us all the way over to neon. So we could even write that as an abbreviated neon atom. This doesn't actually mean the atom changes into neon. Keep in mind that we're only writing electron diagrams. The number of protons would still be 7, and so it would still be called nitrogen. But it has the same electron configurations as a neon ion if you do it like this. It's actually part of why atoms bond, is they're trying to get an electron configuration to be like the noble gases. Now let's look at selenium. Selenium is a little bit further down on the periodic table, down here in our 4th period. The noble gas before that is argon, so that's where I'm going to start, abbreviating argon, which means then I'm going to be able to start on this 4th period with 4s2. Remember what comes next with the D block? You've got to drop down to 3d10. And then we'll go across to the P block where you've only got 1, 2, 3, 4 blocks until you get to selenium. So this would be 4p4. But this is not the selenium atom, it's the selenium ion. That -2 charge has to come from having 2 extra electrons, which would make this 4p6. So it's actually going to carry us all the way over to be like krypton, meaning the electron configuration is similar to the krypton electron configuration. Now let's try magnesium, a positive one. So magnesium is here in the 2nd column, 3rd period. The noble gas before that would be neon, so I'm going to write neon in brackets. And then that's going to allow me to start at the 3rd energy level with 3s2. Now the question is, how do I make a positive charge? You can't add protons, otherwise you would change magnesium into silicon. We don't want that. So instead we have to lose electrons in order for 2 of the protons to be unbalanced. So losing 2 electrons means these 3s orbital, or this 3s orbital would completely disappear. The 2 electrons in it would be gone. So all that you're left with is the neon configuration. The last thing we're going to look at today is something called an orbital diagram. This is very similar to an electron configuration in the sense that the ordering is the same, but instead of grouping all 3p orbitals in one just by writing like 3p6, we're going to break that down and represent each of the separate orbitals as a box. Then we're going to place each electron in that box as an arrow. Here's where Pauli's exclusion principle and Hund's rule really plays a role, because we want to make sure that we're spreading the electrons out evenly within each box set and that we're never putting 2 electrons in the same box facing the same direction. Let's look at the boxes we have set up for these first few examples. Notice that anytime you draw a set of boxes for S, it comes as a single box. That's because S only has 1 orbital. Notice in the bottom corner you have 3 boxes for our p orbital, and that's because the p's always come as a set of 3. How many boxes do you think would come in a set for D? Or how about for F? There would be 5 boxes for D and 7 boxes for F. So you kind of have to know the electron configuration first so that you can draw this setup of the right number of boxes. Now let's talk about putting electrons in the boxes. For hydrogen, since the electron configuration is 1s1, I'm only drawing 1 box with the orbital of 1s. Then I'm going to put 1 electron in it by drawing 1 arrow. I usually always write up arrows first. It's always how I've seen it done in textbooks as well. But as long as you're not putting like arrows together, you should be fine. Most people draw the up arrow first. Then let's look at helium. So with helium, I've got 2 electrons to place in the 1s orbital, right? So the first one would go up, and then the second one would go down. You would never want to put 2 arrows going the same direction in the same box. That would violate our rules. All right, now let's try one that has multiple orbitals. As we look at carbon, we want to fill them 1 orbital at a time. So let's first do the 1s2. So in the 1s orbital, I'm going to place 2 arrows. One up, one down. I know Hund's rule says that you want to spread out electrons, but remember the very first sentence there was when you have equal energies. So each orbital would have a different energy, so we're going to fill them one at a time. The second orbital is 2s2, and now I'll fill both electrons, again going opposite directions for that orbital. My last orbital is the 2p, so that would be what I have here where it comes in a set of 3. I want to place 4 electrons into this orbital. Now that I have an equal energy area, all 3 of these boxes here have equal energy, I will follow Hund's rule and I will spread them out. So my first 3 electrons would be spread out to the 3 boxes. I wouldn't double up until I got to my 4th electron, and then I'd come back here and place it with the first arrow, my first electron. So this would be our electron configuration for carbon. I do want to show you one other shortcut, because when you're writing all of these boxes for yourself, it's kind of a lot of writing. So instead of writing boxes, you can also just use dashes, and instead of writing complete arrows, it's okay to use half arrows as well. So you would see this a lot in some of your more advanced books too. This means the exact same thing. You can just use dashes instead of boxes and half arrows instead of regular arrows. Any combination of this is fine. You just want to be able to show where the electrons are in the orbitals. Alright guys, I know this was a tough lesson. Thank you for hanging in there. Make sure that you bring any questions that you have to class. This is the end of Notes C for Unit 2. There's one more set of notes for periodic groups and trends, which will be Notes D for Unit 2.